It is worth adding a little bit more detail to this heat transport business in the ocean. One of the more important things about the thermohaline circulation, obviously. So think about the ocean meridional overturning that we are thinking about from the equator to the deep water formation site and back. So there is cold sinking water, and the surface waters are being upwelled broadly over the region and being warmed up and being moved towards the deep water formation site. And it is this difference of warm water going north and deep cold water going south that generates a strong northward heat transport, right? Because you are moving heat here and it's being lost, and cold water is going to be converted back into warm water. Writing again our heat transport, H is the horizontal heat transport. Heat capacity of the water integrating from bottom to top, the density times the meridional velocity times the potential temperature, let's say, times dz, the depth over which we are integrating. You can write the stream function here. So define rho ref v as a non-divergent flow, horizontally non-divergent flow. So vertical gradients have to be equated to the meridional transport. So rho ref v becomes minus d psi 0 dz. Replacing that, we get d psi 0 dz, theta dz, and we can rewrite this as d theta dz, but integrate this out because we can just set psi 0 equals rho ref psi MOC. Okay, so you can set the value of psi 0 to be 0 at the bottom, and the integral just becomes the value at the top, which is equal to this one, right? So it's a very simple manipulation with some approximation. So now you can integrate d theta dz just becomes d theta. So you can integrate it in the energy space, like isentropic surfaces that we talked about in the atmosphere. We have here the potential temperature space going from theta at the bottom to theta at the top. And just make sure you understand, you go through these equations. They are very simple. We didn't do much except assume a few things, give the stream function a form. It's good to do that because meridional stream function, zonally average meridional stream function in each basin can be done, because if you integrate from top to bottom and there is no bottom vertical flow and top vertical flow, you can assume obviously it becomes horizontally non-divergent, which allows you to write a stream function. And then you can do this for the ocean as heat capacity times delta theta, the difference between the top and the bottom, times psi 0 max, the maximum stream function. Okay, if you look at the stream function, which maybe I should show, which I will, actually I should have done that, then the maximum is not actually near the surface. We can replace the averaged transport with a maximum stream flow stream function with the temperature difference between the top and the bottom. In the atmosphere, we had a similar expression with Cp, because obviously it's a compressible fluid, delta theta A and psi A max as well. So Cp delta theta A we had written in the atmosphere as Cp delta T plus G delta Z plus L delta Q, and we had said that the atmosphere has the dry static energy and the moist static energy together. So this part was essential for producing the little northward transport in the Hadley cell, because the dry static energy was basically moving towards the equator instead of towards the poles. Okay, you remember that? You can plot this now in the depth space or the temperature space, and you can see that they look different. You can see the STCs, or the Ocean's Hadley cell. This is the global ocean, so we have averaged in the zonal, even though it doesn't make great whole lot of sense, but we do it nonetheless. And you can see, okay, this is the meridional stream function you can think of, right? So here is the sinking and deep water formation in the North Atlantic, and here is the sinking and deep and intermediate water formation in the Antarctic Southern Ocean region. And you have the STCs, and you have the cross equatorial transport of the bottom water, cross equatorial southward transport of the North Atlantic deep water, and the upwelling of the North Atlantic deep water in the Southern Ocean between the Antarctic intermediate water and the Antarctic bottom water. Because we have integrated it zonally, it doesn't look very clean, but those are the basic features. So there is cross-equatorial flow here. So basically, ocean is moving heat across the equator to the north into the North Atlantic deep water formation site, which is important to remember if we remember that the available potential energy in the ocean is being mechanically produced. In general, the ocean is mechanically driven by the winds, and hence, if we look at the average temperature of the southern hemisphere versus the northern hemisphere, we are actually moving heat from the colder hemisphere into the northern hemisphere because it's mechanically being forced to move up a gradient of temperature. Okay, in the temperature space it looks different. Still, you find the cross-equatorial transport here. You get the symmetric cells around the equator and the cross-equatorial transport of the deep and intermediate water. Okay, this has got an advantage because now it reduces the whole circulation into two cells as opposed to multiple cells here. Okay, so you got one cell and the other cell, and you still got the cross-equatorial transport. So this is a nice work again from John Marshall's group. For the atmosphere and ocean together now, this is the ocean and this is the atmosphere. You can see that again you end up with these two cells. The ocean, the atmosphere is moving heat into the southern hemisphere in the Hadley cell because the ITCZ is to the north of the equator. What is it doing? Basically, it is compensating for the northward energy transport by the ocean. Ocean is mechanically being forced to move heat across the equator into the warmer hemisphere. It has to be moved back for balance, and ITCZ does that. It's called the energy equator for that reason. We didn't go into the details, but you can see what we mean a little bit here. Okay, here is John Marshall's paper. Arnold Chaya and John Marshall wrote these nice papers. So that kind of should conclude our story, except that we have to add also the freshwater transport. We are when the ocean currents are having this thermohaline circulation and there are evaporation and precipitation changes happening. So we have negative E minus P over here with lots of precipitation and here in the storm tracks. And we have positive E minus P in the subtropical gyres. Then there is also a salinity or freshwater transport being done by the ocean. It's often referred to as the oceanic hydrological cycle as opposed to the hydrologic cycle on land that we typically talk about. So just like the SST interpretation, the salinities have to interpret it in that sense. So this is how the freshwater transport looks. Remember, these are, be careful, these are negative numbers, so they are southward transport, and there are various estimates. These are all estimates, by the way. It's not easy to measure them at all. Okay, the uncertainties can be large. You can see here the standard deviation from the data. So these are different estimates, and you can see basically there is southward freshwater transport, which means salt is being moved northward, which explains these high salinity here and high salinity there. So to create deep water, we are moving salinity north, and which means freshwater south. Okay, that's kind of the main story of thermohaline circulation. Very interesting. Mechanisms are complicated, but still can fit into the Taylor-Proudman theorem and Taylor-Column theories we looked at. They explain most of the features, but again, these are done in a mean sense without accounting for any of the eddy transports. We don't know much about them anyway, whether in the ocean eddies play any net role in moving heat northward. There are studies that argue that they do, but it's not as obvious as in the atmosphere. Okay, so the mean meridional circulation in the ocean is strong, but remembering that the ocean doesn't do much heat transport north of the subtropics, then we have to just figure out what the eddies are doing beyond the subtropics in the ocean. There are a lot of eddies. Are they really moving energy to the north? In which case, that would be something adding to the northward heat transport by the atmosphere in the northern hemisphere and southward in the southern hemisphere, right?